of this session. We have two presentations here, and they will follow the same time slots as regular. And at the end, we can have some time for additional questions. So first two presentations, then we also have some additional time for additional questions at the end. The first speaker of today is Dr. Josef Schnarch from Oilerian Solutions. He will be presenting a talk on fluid structure interaction simulations in OpenFOAM with hyperelastic material models for aneurysm modeling. So please, Josef.
Thank you, Hakan, for the nice introduction. So hello, everyone. My name is Josef Schnarch, and today I'm going to talk about fluid structure interaction simulations in OpenFOAM for aneurysm modeling. So this is something for biomechanics. So the basic idea of these simulations is to understand the behavior of aneurysms in the brain, so-called cerebral aneurysms, because it is very problematic to treat them, and we want to understand them with simulations. So the important key features is that we have to correctly describe numerically the material behavior of both the fluid, so the blood, as well as the material of the blood vessels. And this is the big challenge, because the blood vessels can vary from old people to young people, female people, male people, and we have to have a correct model which can describe all those blood vessels. So here, the solid mechanics part is more important to test whether we can describe the solids correctly. So for that, we use FSI simulations in OpenFOAM, and for that, we use solids for foam. You heard today in the fluid structure interaction session by Iago about this library. It was here in the bottom, you can see the first reference. It was implemented by Philip Cardiff et al. And so it is based on the foam extends solids for foam models. And what we did with Philip is that we ported it to 1812 and 1912 and 2012. We are currently porting it to 2012, and we replaced mostly GGI with AMI and added a couple of additional features to it. And also I added a couple of non-linear models that are not available in the foam extend version. So Iago already talked about the basics of the fluid structure interaction in solids for foam. It is the same basics, only that I'm using version 1912 here, and I'm using different solid mechanics models. But the basic idea is that you solve your fluid equations in a time step. It's very similar to row pimple foam. Then you out of the fluid equations, you calculate the pressure as well as the viscous stress. Those are interpolated onto the wall, to the interface between fluid and solid, and they are interpolated onto the solid mesh. And on the solid mesh, this pressure and viscous stresses are used as body forces. And then on the solid mesh, the displacement field is calculated with the partial differential equations. Those are interpolated back to the fluid mesh, and the fluid mesh is moved by those displacements. And then you have to do some under relaxation in this regard. And then once you reach a certain convergence in a time step, then you can go to the next time step. So Iago showed you these equations. So linear elastic models, here you have the mass and acceleration. And you have the stress integral as well as body forces. And here for linear elastic models, you can assume the stress to be proportional to the strain, and the strain is proportional to the displacement U. So if you enter epsilon here and then sigma here, you have a partial differential equation for U, the displacement, here also U, and then the body forces. So it is easy to solve the linear elastic material models. For the nonlinear part that Iago talked, and I'm talking about here, the real difference between the material models is how you calculate the sigma. And in Iago's talk, he used Mooney, Rivlin, Yeo, and Fung, if I remember correctly. And I personally implemented the so-called reduced polynomial model as well as the Ogden model, and used those for simulations. So we did do also experimental validation for or the implementation of the basics with solids for foam plus my material models. And for that, we used two geometries in experiments as well as in the simulation. Here we used a channel with 4 millimeter diameters and a wall thickness of 0.5 millimeters with a length of 80 millimeters. So this is a larger blood vessel, and we did a solid channel. And what we also did is a wall thickness change, where in the middle third we reduced the thickness from 1 millimeter to 0.5 millimeter. So there is a thickness change in the geometries. And we, in the experiments and the simulation on the inlet phase, gave a time-dependent pressure profile curve. First, a realistic blood pressure curve from literature, as well as a trapezoid curve just to test the experimental setup. For the material in the experiments and as well as in the simulation, a polymer called dragon skin was used, which is very similar to blood vessels. And here, what you can see are the results of the validation. So on the left-hand side, you see the strain of the blood vessel. The blue curve is the strain in the experiment. The orange curve is the strain in the simulation. And on the right y-axis, you can see the pressure in the experiment. So the green curve is the pressure in the experiment, and you can see that the strain in the simulation follows nicely the experimental curve, because I just copy pasted from the Excel file from the experiments the pressure curve onto the inlet. And because both the fluid as well as the solid are almost incompressible, even small oscillations in the pressure can be seen in the simulation results. In the experiment, in the measurement of the strain, there is a certain lag, a time lag, as you can see. And also, there is a small difference in the maximum between the experiment and the simulations, which is less than 1% of strain. But to quantify this difference, I'm going to just show you a second set of experiments. So no additional simulation, just a second set of experiments, just to see the difference between experiment and experiment. And as you can see, the two blue curves have almost the same difference as the difference between simulation and experiment. So also in another case with the change with wall thickness and the trapezoid curve, here you can see the pressure curve, again, the green curve, and then the strain in simulation and experiment. Here the maximum values are met nicely. If I blend in a reference experiment where the maximum pressure was almost the same, here we measure also in both experiments the same strain, and the simulation gives also a very good estimation of the maximum strain. And as you can see here and here, the simulation is usually between two experimental curves. So the basic conclusion here is that our simulation can describe the process just as well as any experiment would. So the deviation between simulation and experiment is the same as between experiment 1 and experiment 2. Okay, so now after we validated this, we can now bring this to the real-life application of a real-life aneurysm, which you can see here. We got this out of a CT scan with a wall thickness of 0.3 millimeters, and the overall height is 22 millimeters. So this geometry is a bit smaller than our validation geometry, but the same order of magnitude. And as you can see here in this graph, we use the Ogden as well as the reduced polynomial model for the simulation here, and also the linear model. And as you can see, after a strain of approximately 20%, the linear model fails to describe correctly the model. The reduced polynomial and the Ogden model were fitted from from experimental data. So those are describing the material behavior better. And as so for a certain stress, so for example, a certain pressure, blood pressure, at higher strains, the strain is overestimated by the linear curve compared to reality. So here you can see the references to the realistic blood pressure curve that we utilized here. And then if we go to the simulation results, maybe it's a good idea to show you a video of that, then you can see more. So left, you can see the linear elastic model, then the two non-linear elastic models. As you can see, the maximum is overestimated by the linear elastic models of the displacement, and this is not warped. So this is the real life displacement of 1.3 millimeters. So this is a considerable displacement. However, as I mentioned, the linear elastics, the simple model overestimates the displacement here. And if I go back to the presentation, then you can see that here the maximum is 1.3 millimeters, and with the nonlinear models both calculate a value of 0.75 millimeters. But it is still a considerable increase if you consider that the thickness is 0.3 millimeters. So it is highly nonlinear for this aneurysm. And then if we go in the last slide onto the stresses, you visualize the stresses, then you can see that I showed you here between 0 and 100 kilopascal. The maximum is actually at 250 kilopascal, somewhere here in this location. And we expect failure at 431 kilopascal. So the simulations suggest that there is not going to be failure, but still 250 kilopascal is not very far away from 430. So it is in the same order of magnitude. So this aneurysm could be problematic. It is not far away from the threshold model. And with our model, these simulations are now possible, and the models were validated. So they resemble the reality. So this is exactly what I just mentioned, that we ran transient FSI simulations of aneurysms with hyperelastic nonlinear models. We even did some abacus verification cases, but I didn't have time to put those slides in today, unfortunately. And with our FSI simulations, we are able to predict wall displacement as well as stresses and estimate failure conditions. Yeah, so that was it. So thank you for watching, and I hope that there will be some questions.
Thank you very much. We have a couple of minutes for questions now, and if we don't manage to finish them in this time, then we can continue with this after the next presenter as well. If you ask more questions from you about Joseph Nair's presentation, please state that it is for his presentation. But let's start here with the first question. Why does the channel have a variable wall thickness?
It is just to add, this is realistic, so blood vessels can be thinner and thicker, so just to have an additional difficulty level for the validation. This is just the only reason to have another difficulty level.
Yeah. Did you experience any convergence issues when using Eichen's relaxation for the FSI coupling? And
of course, of course. But you have to fine-tune the numerics. So you have to really find the best under relaxation values, the best tolerances, number of correctors. So of course, like everybody has some problems, numerical problems, but it's testing and trying mesh quality and so on. So yes, but now I found them, and the simulations are running nicely.
And then the Reynolds number that you had in the flow?
I don't remember that, so I have to look it up. So as I mentioned, it is a pressure-driven flow, like in real life, and we took the pressure from literature. I'd have to check the exact Reynolds number. I don't know it by heart, sorry.
Okay, maybe you can answer that later. Did you consider non-Newtonian effects? Is the flow Newtonian or non-Newtonian? Does the non-Newtonian effects have any?
For the validation, the fluid was water, so there it is non-Newtonian. For the blood, you can use, we tried non-Newtonian fluid, but the difference is not very big for these kinds of flows, because the pressure is isn't changing abruptly. So you can assume to be Newtonian as well. Yeah, so the problems are some on the solid side here in this problem.
Yep. How long did the real aneurysm case simulation take to run?
Linear elastic runs on my laptop within half an hour, 45 minutes. The non-linear ones do take longer on a laptop, a couple overnights, but on a workstation, it's a couple of hours.
Let's see. Are aneurysm simulation used to guide surgical procedures or evaluate surgical risks?
Not until now. I mean, in 2 projects where this could be an output, but not at this point. So I'm not doing anything for hospitals at this point.
Did you have a turbulence model? Did you include compressibility, or was it assumed to be incompressible?
Yes, turbulence, yes, and it was compressible, so it is raw pimple foam or a derivative of that, and with a very, very small compressibility, like water.
Okay, I think we can do the last question as well. Could you say something about the smoothing applied to the segmentation of the patient's geometry from the CT data?
Unfortunately not, because this was done by the doctors which are involved in the project, and I just got an STL file. So unfortunately not.
Okay. So I think that was all the questions actually, but if you have questions for Joseph, you can ask them, but please then state that it's for Joseph so I can distinguish them from the other talks. Then we can have a look at those after the next presentation as well. So thanks again, Joseph.
Yeah, thank you.
And now we will move on to the next presenter, which is Mr. Changyong Lee from Center of Applied Space Technology and Microgravity in Bremen. And he's going to talk about CFD studies of the dynamics in gastric contents induced by human stomach motility. Sorry.
Thanks. Hello, everyone. I'm honored to have a talk here. My talk is the CFD studies of the dynamics in gastric contents induced by human stomach motility. The objective of this study is to better understand the effects of gastric motility on the dynamics of liquid gastric contents inside the human stomach. While this presentation mainly focuses on the mathematical modeling. It includes 4 sections. They are background, modeling, results, and conclusions. Human digestive tract is a complex organs and glands. The main parts are mouth, esophagus, small intestine, and stomach. Most of the digestion happens in the stomach. Understanding the digestion mechanism in the stomach can give better insights for the design of functional foods. Human stomach is a J-shaped muscular and hollow organ in the upper digestive tract. The most important functions of stomach are mixing and empty of gastric contents. The key factors that influence the functions are gastric motility and gastric juice. They will be explained in details later. Gastric ragi are coiled sections that exist in mucosa and submucosa layer in the inner stomach surface. Ragi allow the stomach to stretch in order to accommodate large meals and help to grab and move food during digestion. The gastric wall is around 5 millimeters in thickness. and which is composed of 4 layers. Gastric glands are responsible for the secretion of gastric juice. They located in the upper part of the stomach wall. Some previous numerical studies reported the retropulsive jet-like motion. Well, how does the motion affect the mixing in the stomach needs more understanding. A 3-dimensional human stomach model is used in this study. It has a similar characteristic length as real stomachs. The inlet of the stomach is neglected with the assumption that the food will not flow back into the esophagus during the digestion. The figure shows how was the geometry was constructed. The imaginary center line is equation driven. The frames of the stomach are constructed with a series of circles. These circles have different diameters and they are perpendicular to the center line. Gastric motility includes tonic contraction and anter-contraction waves. Tonic contraction is a weak continuous contraction of the whole stomach wall. Anter-contraction waves are peristaltic contractions which initiate at the middle body and travel towards the pylorus. TAC is a terminal anter-contraction which occurs when ACW reaches the terminal antrum. The gravity acts vertically. Gastric juice is a digestive fluid. It plays a key role in digesting proteins. In our simulation, the gastric juice was simplified as water and hydrogen ions. They come out from this blue layer where the distance from the wall is smaller than 3 millimeters. Well, the region the region where the distance from the wall is smaller than 5 millimeters is set as a porous media, which is used to model the effect of the wrinkles at the stomach inner surface. This table shows the main parameters of the stomach. For example, the volume, the pylorus diameter. As can be seen from this table, our parameters are within a reasonable range. This table shows characteristic parameters of muscle contractions in different numerical studies. It can be seen that tonic contraction was neglected in most works in the past. However, it's hard to specify the stomach emptying rate without the tonic contraction accounted for. Both tonic contraction and anter-contractions are taken into account in our study. The gastric contents are supposed to be composed of water and soluble food species. Food species have different densities, viscosities, and diffusivities with water. The solver was developed based on the Bosniak approximation for buoyant flow. We assume that the density of the gastric contents, the variation is small, so the gastric contents can still be treated as an incompressible flow. The conservation equations equation of mass. Sg is the source term due to the secretion of gastric juice. Sw is a source term due to the expansion and shrinking of the wrinkles. The governing equation of momentum. Phi is the local porosity. SPI is the source term of momentum due to the porous media drag force on the fluid. The food species is modeled by this scalar transport equation. The transportation of hydrogen ions is accounted by this scalar transport equation. SCH is the source term indicating the increase of hydrogen ions due to the secretion of gastric juice. We use the dynamic mass method to control the wall movements of the stomach. Here I will not talk too much details. If you are interested, we can talk it afterwards, or I can put a link of the paper. For movement of ACWs and TACs, we designed a cosine shape function to model its deformation. For toric contraction, we define the shrinking rate of the entire wall by its emptying rate. When the dynamic mass method is adopted, the integral form of the conservation equation for a general variable psi become this form. We have done a mesh sensitivity study with different meshes and also compare the results qualitatively with the published works. The developed CFD model is used to simulate the emptying and mixing process for 3 different liquid foods. They are water, orange juice, and whole milk. The physical properties of foods used in the study are shown in this table. It should be noted that they have different energy amount. A published paper suggests that the gastric emptying is controlled to be 2 to 4 kcal per minute. In our simulation, we use a constant emptying rate, which is 3 kcal per minute. Here we show vortex structures in the water emptying process. They are colored with vertical velocity. The effects of TAC are investigated. The contraction of TAC creates retropulsive jets. This flow phenomenon was also found in other research works. It should be noted that in the previous study, this type of flow was captured when the pylorus was closed. Our numerical results show that it also occurs when the pylorus is open. We can also see small vortex structures in the upper region after the TAC starts. In this figure, in this figure, we show the change of average the kinetic energy with time. As can be seen, the periodically generated TAC cause periodic oscillations of the kinetic energy, and the TAC can obviously increase the average the kinetic energy. Here we compare the mixing effects of TAC. The pH is more uniformly distributed when TAC is considered, showing that the TAC can enhance the mixing of the gastric juice. TAC can push back the hydrogen ions into the upper region of the stomach, which makes the pH lower. This is beneficial for the digestion. Here we compare the mixing for 3 liquid foods. This figure shows the history of mixing rate. The value of mixing rate increases slowly for 3 foods. This figure shows how the average pH values in the stomach evolve with time. For 3 liquid foods, investigate here. The pH for whole milk decreases fastest due to its slowest emptying rate. Now come to the conclusions. TAC plays a key role in the generation of the retropulsive jet. This type of flow was also occurs when the pylorus is open. TAC enhances the mixing of liquid gastric content and reduce the pH in the stomach. Food properties have significant effects on the transportation of hydrogen ions. The most important task in the future is how to validate the numerical results quantitatively. Thanks for your attention. I'm happy to take questions.
Okay, thank you very much for your presentation. So we have one question, and while we take care of that question, then the rest of you can also ask some questions. So we have the first question is the geometry of the stomach looks fantastic. How did you generate the mesh? Was it generated using SnappyHex mesh, CF mesh, or other meshing tools?
Thanks for the question. The mesh I used was generated by SEM, but I also generated the mesh by SnappyHex mesh. I think they both can generate good meshes.
Okay. Okay, do we have any other questions? Meanwhile, I can perhaps, also you can ask questions to Joseph that presented before, if you like. I can ask a question here then. As I understand, you prescribed the contraction of the geometry by mathematical functions.
Yeah, right.
Yeah, and is it only in some part of the domain where you have the contraction? Can you point out that again, because I probably missed it a bit.
Because the gastric moiety, there are 2 different kind of gastric moieties. It's the one is the kind of one is the cosine shape deformations. So we use this equation to deform the stomach wall. Another one is the entire contraction of the stomach. It means the stomach is shrinking during the digestion. By contouring the shrinking rate, we use this equation. The stomach shrinks based on how much food retained in the stomach.
Okay. So it means you don't have any, like in the previous presentation, there were fluid tractor interaction simulations, but here you don't include that in that case, I guess, in any part of the stomach.
No.
What about the surface properties? Because as we saw in one of the slides, this the tissue of the stomach is very complex. I think it was in that slide, you see the right picture, for instance, you see that it consists of many layers, and also the internal part of the stomach has probably some very special features. In your model, I guess you modeled that as solid wall, or did you have some particular wall model that?
We didn't use special turbulent wall models. We model this wall porous media region.
Okay. Mm-hmm.
It means we add some source terms into the momentum equation.
Yep. Okay. Okay, do we have any more questions? If I don't see any questions, at least in the platform here, even if I update. So we can ask questions to Joseph as well, or to this presentation here by Shangyong. So it seems like there are no more questions, unless you are fast with your fingers to type your questions. So in that case, I thank both presenters, and I thank the audience for listening. And I guess this concludes the first day as well. So see you tomorrow then, all of you. Thank you.
Yeah, thanks.
Thank you. Bye.
Bye.
Bye.